So, this is the last in sense of the spectral discussion. Of course, there is one last which is spectral factorization, which is kind of reaching the peak. Beyond that there is a valley. Anyway, so we have talked about random aperiodic processes until now, but before earlier in many other lectures we have said that there are random processes that are also periodic. Now, if it is hard for you to imagine a random process that is periodic, you take a number of examples that you see in real life, bus schedules abroad, not here, but or any other systematic schedule that can be followed. In India we have a number of reasons why we cannot really have, some buses do indeed come on a periodic schedule, but if you take a bus arrival schedule and if someone says that on the average bus comes every 15 minutes, that is kind of a periodic process. Why is it not periodic in the deterministic sense? Because it does not come exactly every 15 minutes, right. There may be some deviation from the 15-minute schedule to the left or to the right, but on the average it stays on the 15-minute schedule. That is not how we define a random periodic process, but that should tell you that there are processes that are periodic and also have some randomness in them. Now, there are many other process examples also, but the question is what kind of mathematical models can model the behavior of such random processes. There are a number of models and the classic model is a sign embedded in noise. So, I say that yes, there is an underlying periodicity, but there is noise riding on top of it, which does not make it periodic in the deterministic sense. That is one way of looking at a random periodic process. Now, is there any other model for a random periodic process? And the answer is yes, there is yet another model for a random periodic process, but before we do that, let us first define what a random periodic process, and we will use the term harmonic to denote random periodic processes. Once we know the definition of a harmonic process, then we can turn to models for harmonic processes. Again, what is the idea here? The idea is to detect periodicities in random processes, right, and a number of meteorological phenomena are like that, your El Nino effect or any other climatic phenomena have number of periodicities embedded. You take sunrise for example, right, there is a periodicity. You take temperature variations in a day, it will have some periodicity and so on. So, how do we detect the periodicities, and we need, for that purpose we need mathematical models, and for that purpose first we need to define what a harmonic process. So, you see theory is very demanding, but it helps you because you know the framework in which we are operating. So, I will go past the motivation and straight away go to the definition of a harmonic process. It is good to compare this definition with that for a deterministic process. For a deterministic process, periodicity is very straightforward. If I have a deterministic signal, then it is periodic with period Tp if there exists, in fact we use n p, if there exists an integer np such that x of k plus np is x of k, right, and np then is said to be the fundamental period. So, the definition attaches itself to the signal itself, whereas the definition that you see for a harmonic process here does not attach itself to the signal. Why is that? In the case of random processes, why are we not defining in terms of the signal? Yeah, because then it will apply only to that realization perhaps. For another realization may be different. The answer is always for a random process we are looking at a collection of signals. It is an ensemble that we are looking at. So, it makes sense to define periodicity as an average property like we have always done before, even for the spectral densities, right. So, there are a number of definitions that are equivalent for a harmonic process. One of the standard definitions is that a signal Vk is said to be periodic if the expectation of the mean square error is 0. Sometimes the temptation is, can I replace this with this? For a random signal, can I say it is periodic if this is satisfied? What do you think? First of all, it has to be stationary, that is required for a harmonic process. We say it is the minimum requirement, it should be stationary. Generally, the temptation is to define a random periodic signal in this word, because we say for a deterministic signal it is sufficient to look at one realization, because that is the only possibility. Now, I want to look at, for a random process, I would look at a collection of realizations and use the expectation property, right, or the average property. Can we use this definition for defining a periodic process? Yes or no? What do you think? Yes? Sure. Think about it. There is a trap there. This is satisfied by any stationary process, right? So, by this definition, every stationary process is periodic. Am I right? Why should this be satisfied by any stationary process? Mean is invariant with time, correct? So, any stationary process will satisfy this. So, this cannot qualify to be a definition of periodicity, even if you were to argue that I can come up with this definition. Of course, we can go deeper into why this definition holds, but at least I have shown you that a natural extension of this does not result in a periodicity of random processes. A natural extension, in fact, I would say more than the definition that I have given you in equation 3, it is the corollary one, that is equivalent one, not corollary, the equivalent condition that I have given you, which says that the autocovariance function is periodic, is a lot more appealing. You say when the correlation structure has a periodicity in it, then I can think of the random process to be periodic, right? And of course, there are two other definitions. But now let me ask you, why do we have to consider this periodic process separately from a periodic process in terms of spectral analysis? What is so special about this? Yeah, it does not satisfy. That is why when I erased everything, I left this alone. This is not satisfied by a harmonic process, right? Because autocovariance function does not decay, it is periodic. Same thing that we discussed for periodic signals. We said a periodic signal is not, if you take a periodic sequence, it is periodic, it stays forever. It does not have a Fourier transform. In fact, it does not make sense to think of a Fourier transform, because when I have a periodic sequence, now we are only talking of sequences, I can think of it to be synthesized from sines and cosines of the fundamental period and harmonics only. Why should all frequencies produce it? So, that is why here for a harmonic process we do not talk of spectral densities, just like we did not talk of spectral density for a deterministic periodic sequence, correct. So, once you reapply and recall the theory that we have learnt for a deterministic periodic sequence, you can apply that to the autocovariance function. So, now the autocovariance function would have a Fourier series expansion. Okay. Now, one of the models, in fact, we will continue this discussion tomorrow, I will just take one more minute. One of the standard models for harmonic process, we have looked at the definition now, and it suffices to remember that a harmonic process is one that is stationary and whose autocovariance function is periodic. Now, what kind of mathematical models can explain such phenomena? One of the standard models that is used is a sum of sinusoids with coefficients being random, but not any randomness. You cannot have arbitrary, because one of the requirements is it should be stationary. If you take the expectation of Vk, what does it amount to? If you take the expectation, what happens? Does it come out to be 0? You have to be careful. Remember, cosines and sines have no randomness in them, only the coefficients may have some randomness. So, you want it to be stationary, and one of the ways to assure stationarity is to have A and B, these coefficients, to be random variables with 0 mean. Any other value will produce a time varying mean. So, that is the first requirement. The second requirement is that A and B should be independent random variables. We are not proving that. In fact, let me just tell you that another way of writing, the standard way that you would see is this. This is another model for a harmonic process where A is random, a random variable, and phi is a random variable, or sometimes phi alone is random variable and A is not random. Phi, in fact, you can show that if phi alone is random, and what kind of random variable should it be? It should be a uniformly distributed random variable. Phi should have uniform distribution in minus pi to pi. If this is the case, then you have, again, when you expand, what do you get? When you expand this, you get this, right? Of course, I have written this for one frequency, maybe omega naught, but if you have many such frequencies contributing, remember we cannot have a continuum, it is a periodic process. So, when you have many such discrete fundamentals plus harmonics, you get the same model that you have here. It is much easier to actually consider this model for a reason I will tell you later than this model, although both are equivalent. You think about what is the difference between this model and the other. Theoretically, there is no difference, you can show they are interconvertible, but one prefers the second model, that is that you see on the screen, not on the one that on the board, and you impose that A and B have 0 average and are independent random variables, and then you can show that the autocovariance function has this kind of an expression. That is fairly straightforward. You start with the given time series model and show that. What you should observe here is that the autocovariance function has been given a Fourier series expansion, correct? Why do not we have e to the minus j? We will answer that and adjourn. Because autocovariance function is symmetric, right? I can only expand a symmetric function in terms of even functions, not odd functions. Everywhere it is common sense, we are not learning anything new every day, but it is just interpretations and some subtle points. Okay. So, with this we will close today's class.